class, not had class. So in case you've forgotten where we left off exactly, the last thing we were doing was making the model of our universal joint, right? So we decided, we looked at this model, we figured out there's 3 distinct parts, and kind of the big new thing that we're trying to do starting out is modeling parts by looking at a drawing. So we went through an example, and that was this like clevis for, I guess, the actual coupling part of the.
Wait, we were supposed to create the stick at the end?
Right, so if you mean this rod, I did show that in the demonstration, but I did go pretty fast. So
there isn't a rod. Because I wasn't supposed to put the rod in between the 2 sides, right? Like, confused.
So this is what the part looked like at the end of last class. So I'm not sure if the recording was posted, but if it was, this is as far as I got. So well, this is the completed part. So we do have like a full demo of how to get this far. If you, I guess, still have any questions, mainly this is what it should look like. So there's like a rod that comes out the back here. And
how do you make that rod? I don't have that rod, and I have the 2 sketch. Oh, you have sketch 3.
Right, so all I did was I sketched a circle right at the center of this rectangle.
Where am I supposed to put the sketch?
And like I said before,
which side do I make it? For the sketch 3, do I make it the right side, the front side, the top side?
Right, so whenever you create a sketch, you actually have the option to place that sketch on basically any flat surface. So even if you don't know, even if it doesn't happen to be one of the top, front, or right planes, you can actually create a sketch on any of these flat faces. Okay. So if your face like corresponds to this bottom of the fork here, if that doesn't correspond to top, front, or right, you can actually just click on it and it'll create the sketch right there. Anyway, what I'll probably do is just do a really quick, like, kind of solutions walkthrough of how I would do these 2 parts. And presumably you've already done it, so you can just use this as like a check against what you did, make sure everything makes sense. But if you had some trouble, you can see what I'm doing, and hopefully that answers any questions you had. Or maybe you'll see like a different way to do things. And then in the event that you weren't able to complete everything, I'll probably just upload the files that I have to the Google Classroom, and you can just download them to do the second part, which is going to be assembly. So really quick, let's just go back to the document that we started last week for this project. So it probably has your clevis in it. Yes, Henry?
So you're just gonna post it so we can copy, so you can copy?
I'm gonna post the part files so that you can do the assembly while I'm showing the assembly, which is the main like subject for today. If you actually have the parts, you should use the ones that you already have, of course.
Okay.
Right, so clevis, hopefully we're all good. I did show everything that's on this clevis, so.
I need the clevis for I need this rod for the clevis.
Right, so yeah, you can take this time. Maybe you don't need to watch all like the walkthroughs I'm gonna do. You can take the time to add that.
No, because like I don't know the dimensions.
Right, all the dimensions are on the drawings, which are on the slides, which are on the Google Classroom. You can find them here, so feel free to join me on this document. Right, so bearing cross, that's this guy over here. Main thing here, hopefully as you're working through this, you realized it's basically 2 cylinders that go through each other like a cross, right? And so the diameter of the cylinder is the same, the lengths are the same. And I know that because of my lines of symmetry. So I know that the diameters are gonna be 1/4 inch or 0.25, and that the length of each one is going to be 1.5 inches. So knowing that, this is pretty straightforward, right? I think I started this when I was going over the hints at the end of last class, but the way I would do this is I'd sketch a circle first, put a dimension on it, 0.25, And then what I was hinting at last week is that there's actually an option to do what is called a symmetric extrude. So instead of just going one way from your sketch plane, it'll actually go both ways, symmetric, up to your desired length. So if I do this, the advantage here is that now the center of my part is still at the origin, but I can just type in the number for the length that I want. So it's just like a normal extrude. It's just that it keeps your center right at your sketch plane. So I'll do that, and then I'll do the exact same thing. So it's pretty simple. Once you know the trick, it's a very simple part, right? Let's draw another circle, but this time in one of the perpendicular planes. And then I'll toss a dimension in there. Again, 1/4 inch. Do my extrusion. Again, make it symmetric, and 1.5. So just like that, 2 features, 2 sketches. The sketches are nothing weird, it's just circles. And I have my part, right? It's my bearing cross.
I have a question.
Yes.
For the clevis, like, how do you do it? Because like, I don't know how to attach, I don't know how big the circle's supposed to be.
So again, I see you're on the slides.
Yeah,
so
but
on this drawing,
how big the circle is. Like the circle size that's attached to it.
Right. So it is on this drawing if you look closely. You might be looking at this view, you can see there are no dimensions there, but you know you have 2 other views of the same object, right?
Yeah, but it doesn't show the dimension of the circles, of the circles like diameter.
Excuse me, Carrie, sorry for the interruption. I know you are very into it. So however, can you please save the question a little bit later so the instructor can just move forward with his lesson, and I will help you later. How about that? Thank you.
Well, all right, well, to answer the question though, these drawings, I have tested them myself. I can verify that using just the drawings, you have enough information to be able to finish the parts. So in this case, like it might look like the circle doesn't have a dimension on it, but you can kind of picture it in 3D, right? You know, this circle corresponds to this rod here. So on these other 2 views of the object, you kind of have this part that you're looking at. And when you look at the side view here, this feature that you're interested in, this rod, has a dimension here of 3/8 of an inch. And so you can imagine if you kind of flip this view, this would be dimensioning, it's the same thing as dimensioning the diameter of this circle. So that tells you what the rod should be. You can see it is 375. And the last part, that is my stand here. All right, here I'm going to use a tool that maybe I haven't explicitly shown you perhaps, but you don't actually need this tool to create the part. It's just something that'll make it a bit easier. So the basic shape, you have something like this, so like a little, not quite a trapezoid. You have 2 legs, let's say, that are going to be equal. And sure, that's the basic shape of it, right? So we'll put some numbers in there. You know, this part is 7 inches. I'll zoom out a bit. And I know that the angle between these legs and the bottom of it, whoops, is going to be 105 degrees. And I know that the length of one of these legs is 3 inches. So here's where I'll show you something cool, maybe. There's this tool here called Offset. And it does exactly, well, maybe you can't imagine, but based on the little icon, you can perhaps guess what it does. And if you click on some sketch entities with the Offset tool, what it will do is it'll actually kind of create a copy of the things that you clicked on, except slightly shifted in one direction or another. So you can see this faint outline of what it's trying to create. It's going to make a set of 3 lines that are basically just the same thing that I drew, just shifted over a little bit. And so looking back at the drawing, I can see that, you know, what I drew was basically these 3 lines here, the inside of the base. What I want to create are another set of 3 lines that are the outside, these 3 lines. And I know that they're separated by a normal distance of 0.5 inches. So I'll just drag this arrow back. It's kind of like a sketch pattern in terms of the interface or how you interact with it. For the number, I'll just type in 0.5. And it basically does like a lot of the work for me, right? So you can imagine I didn't actually need to do this. I could have created the lines myself and dimensioned them with the normal distance, but this just saves me a little bit of time. So hopefully that's helpful to you. And I'll close off the caps. And here, I guess technically it's not like explicitly stated, but from this drawing, we're going to assume that this cap is like at 90 degrees to the legs that are there. So if I add a perpendicular constraint there, that will be enough to fully define them. You can see now my sketch is all black. Whoops. So last things, I just need to extrude it. So the width of this is 2 inches, as you can see from the top view. So I'll extrude this to a depth of 2 inches. And then the last step is to add these 2 holes. So looking at this part of the sketch, I can see that from the end of the at the end of one of the legs, the hole is 1.5 inches from the end. And looking at this top view, I can see that the holes lie kind of on this line of symmetry, so they must be at the middle. So what I'm going to do, here's an example of what I was talking about. You can place a sketch on any flat surface. I can actually just place a sketch on this surface, even though it's kind of at an angle with respect to my original coordinates. And then all I need to do, if you want to, you can just view normal to, and I'll create my hole. So the dimensions, the hole has a diameter of, let's see, 0.375. And it's located right at the middle when it comes to its vertical position. And it's located 1.5 inches away from the end. And I can just do that using a dimension and one midpoint relation. And again, since these aren't actually part of my final boundaries, I'm just going to turn them into construction lines so that they don't get in my way. That's my sketch. And I can just take that and extrude through to make a hole. And it's the same deal on the other side. I can just repeat the same thing over again. Oops. And with that, that's the finished part, right? All right, so if you had that all done already, hopefully maybe learned something. At least you learned that the offset tool exists, which is probably going to be helpful in the future. And if not, you can maybe watch that back slowly and go through it yourself if you weren't able to figure it out on your own for homework.
Wait, these videos are going to be recorded and posted, right?
Yes, I believe all the classes have been recorded and uploaded so far on the Google Classroom. So like for the Clevis too, I went through all of that last week, so you can always watch this one and you can listen to me again as I go through the same parts.
I already figured out the Clevis.
Great. So that kind of wraps up that. So at the end of this class, we're going to try to put that together and hopefully get it moving in action. And without further ado, we'll start the new topic for this week, which is going to be assemblies. So you've probably been exposed to assemblies by now in some way or another. The idea is, at least the way Onshape structures it, you kind of have your part studios, which store, or this is where you create a single part, right? A single solid body. Sometimes you can have multiple solid bodies in a single part, but we're not going to worry about that. We'll just say that part studio is where you keep your single parts, right? Like a single unit of the ultimate model you're trying to build. And in a lot of cases, the actual thing that you're trying to make, whether that's say a robot or a car, is going to have a lot of different parts that you have to put together. And the whole objective of creating the model is to see how these different parts that make up the whole assembly kind of interact and move with respect to each other. So that's what the assembly, that's where the assembly comes in. It allows you to put multiple parts together into the same workspace, and it allows you to create a bunch of rules about how they can move relative to each other, and these are called mates. So we're going to do a very quick crash course about different types of mates. You've probably seen many of these, maybe some of them will be new, and to help you kind of play with the different mates. We have this Onshape document kind of that you can view. So I put the link in the chat. If you click on it, it should take you to this document over here. And hopefully that works. If not, let me know. But I will also have it up so you can also just watch. The first of the mates, the most basic one, is the fasten. And so this is the most basic one, right? I like to compare this one to gluing things together. So when it comes to mates, like I said, the whole idea is that we're trying to define rules about how they're allowed to move with each other. And so fasten is kind of the simplest one, because the rule is they're not allowed to move with respect to each other. If you fasten two things together, you've glued them together, you can't move one without also moving the other. So if you go to assembly 1 in the link that I sent you, what you'll find is that when you try to move one of the blocks, you can't separate the two blocks because they've been fastened together. Do you have a question, Henry?
Mine doesn't look like that.
Make sure you're on assembly 1.
Oh. Okay, right, never mind.
All right. So that's a fasten mate, pretty straightforward. Just think of it like glue. And that's all there is to it, right? It's the simplest mate. There's no freedom. The next mate that's very commonly used is what Onshape calls the Revolut. And just like the name implies, it allows revolution, rotation of two parts against each other. So similar to the fasten, this one's a pretty restrictive mate. There's not a lot of freedom that the objects have. If you revolute two things together, they can't actually move translationally. They can't move apart. They can't slide along each other. They're going to be stuck to each other pretty much, except that they'll have one rotational degree of freedom. You'll be able to spin with respect to each other, even though you can't move. So you can kind of think of it like one of those door handles, actually pretty much any door handle that you turn, like a doorknob. You can twist it, but you can't actually pull the doorknob back, or you can't like slide the doorknob along the door, right? The doorknob is stuck in place, it can just spin. So that's the Revolut Mate. It's the second assembly in this document. So watch it go. Right. Next is the slider mate. This one, kind of like the Revolut Mate, it allows you for exactly 1 degree of freedom, right? It's also a pretty restrictive mate, but instead of allowing rotation like the Revolut Mate, it gives you 1 translational degree of freedom. It allows your objects to move in one direction, back and forth. It doesn't let it spin in any direction. And it doesn't let it like move side to side or front and back. It can only move kind of along the path of your sliding axis. So in assembly 3, you can see this piston and cylinder have been mated with a slider. So I can't drag the piston out of its path. I can't drag it so that it wouldn't slide perfectly into the channel. I can only move it back and forth. You have a question, Henry?
Oh no, wait! I forgot to lower my hand.
All right, so that's the slider. Again, so far our mates had either 0 freedom, which is a fasten, or 1 type of freedom. The next mate is planar. This one is not quite as common as the previous 2, but it's still pretty interesting. This one is the first one where you have 2 degrees of freedom. Here, it allows objects to move translationally in 2 directions, both like up and down or left and right with respect to a surface. But there's still no rotation allowed, and you can't move off of the surface. So you kind of are missing that 3rd dimension of movement. So I can kind of think of this like a hockey puck that's stuck to your ice floor, right? The hockey puck, I guess a real hockey puck can like fly all over the place, but just imagine that it's moving very gently. It'll only stay on the surface of the ice, but it can move anywhere on the ice. And that's your planar mate. All right. And last one I'll demonstrate is the cylindrical mate. This one is kind of a combination of the slider mate and the Revolut mate. So you get one of each, right? You get 1 rotational degree of freedom, and you get 1 translational degree of freedom along the axis. So if you go over to assembly 5, this kind of lets you play with it. You can see that I can slide it up and down, and I can also spin it. So this one's kind of like maybe the most realistic one if you have just a unrestricted shaft in a bearing. It'll slide back and forth, and it'll spin. All right. So those are most of the basic mates. That'll probably cover you for most of the assemblies that you're going to make early on. As you get more advanced, there are going to be other mates that you run into and will have to use. But as you encounter the need to use these mates, you can just look up how to use them in the Onshape documentation. You can play with it for yourself. Most mates are pretty intuitive just because we do have a pretty good sense of how objects move if you've ever played with anything in real life, I guess. It's just like real objects, right, on your computer. So the first one is a pin and slot. You probably encountered pins and slots in real mechanisms in real life. This is a little picture of a pin and slot mechanism. So it's kind of like a slider, but instead of just sliding along one axis, you're kind of following a path that's dictated by a channel that has a certain shape. So each of these pins can kind of move along the channels that are cut out for them. Kind of have here is a ball joint type of mechanism. So if you've ever played with a joystick, that's sort of like a ball in a socket. Basically, you can spin, it can revolve in any direction, but it's fixed in place. It's still stuck to the socket. Let's see, there's parallel mates, I believe, in Onshape. That's just, it's kind of like a planar mate, except that they don't have to be touching each other. So it just makes things parallel to each other. Tangent mate, I believe that just brings things, it's kind of like making things tangent in a sketch. It takes objects and it brings them together so that they're touching, just barely touching at the surface. And then there are also mates that allow you to kind of couple the motion of two different mates, in a sense, like mates for mates. So there's gears, racks and pinions, and screws. So you can imagine if you're designing like actual machines that involve machine components like gears, racks, or screws, you can actually model them to have the correct ratios and to like make each other spin using built-in Onshape tools. So that's pretty neat. I won't go into those, but they do exist. So if you ever need them, you can use them. All right. And finally, if you're ever doing something that's a bit more complicated, right? Maybe there's a lot of different mates that you have to make, but the entire assembly it has some form of symmetry that makes things easier for you. Maybe it's like a car and the left and right happen to be perfectly symmetric. If you're gonna make all the mates for the left half of the car, maybe there is no need for you to do everything to the right half of the car if it's exactly the same. So just like sketches and just like parts, assemblies also allow you to make patterns. So there's linear patterns and circular patterns, and essentially just lets you, in a situation where you have multiple parts and mates that need to be exactly the same, it'll just create them all to be the same. And they'll also be sort of linked together. So if you move one, they're all going to move together. So the last demo assembly in that document is an example of where you have a circular pattern for your mates. So you can see there's only one mate here, but it's been patterned. The part itself has been patterned, to be clear. And what you'll see is when I try to drag one of these pegs in and out, all four of them will move in and out together. So maybe you can see where this would be useful. It's definitely a lot easier than me having to go in and create all four of these separately, if they're all going to be doing the same thing anyway. Okay, great. Any questions about mates so far? If not, here's another little demo. This one makes use of a lot of the basic mates that we went over in the earlier slides. Some of you, if you took CAD 1 with me and we got to this project, you actually made one of these, maybe not. If you want to look at it, there's a link that I just put in the chat. So it'll take you hopefully to this document, which just is a example of the project, right? I guess this one is not mated. But the one I linked should be mated. And you can just take a look at how the different mates are used. I sure hope they're mated. Let's go to the assembly. All right, they're not mated. Well, in that case, if you want a fun exercise, you can take it upon yourself to try to mate the parts in that document. So if you want to edit it, you click on the link and then you can make a copy of the document for yourself. Let me just show you how to do that. let's see, yeah, if you just click on this button, you can make a copy to edit, and it'll just create a local copy in your own workspace. And so I guess if you want to have some assembly practice and you didn't get to do this project in the CAD 1 class.
Which one's the slider?
The slider is, let me get an assembly.
Like which
This one.
No, I'm just asking which one is it in the first link you shared? Assembly 1, 2, 3, 4, 5, or 6.
I believe it's assembly 3. Yes, this one.
Okay. I think I know which ones to use. I'm gonna try.
All right, so good luck with that. This isn't really the main focus of anything, but just for fun, if you have extra time and you're curious. Anyway, with all that out of the way.
Hey, which one is assembly 2?
Assembly 2 is Revolut, I believe. The doorknob, right?
Yeah.
The one where you can only spin. All right, so if you have any questions about any of the different mates, please ask. And I'm going to take a minute to just upload my versions of these parts to the classroom. And once I've done that, let's see. We'll get started with assembling the U-joints. So also, yeah, feel free to, let me stop sharing. Feel free to take a attempt at beginning to assemble. So as a refresher, you already have your assembly tab probably at the bottom of your document. And from there, the first thing you do is insert part. And so you'll have one of each and 2 of the clevises. All right, let me create material.
Are you supposed to be sharing?
I'm just uploading the parts for the U-joint, and then I'll resume my share. All right, so if you're missing any of the 3, I just posted U-joint parts, so you can download these. I think I demonstrated, actually I'm not sure anymore. I may or may not have demonstrated how to import a part, but the way you do it is you hit your plus sign at the bottom here, you hit import, and that will just take you to File Explorer if you're on a PC. And you can just navigate to wherever you downloaded the part, click on it, it'll take a minute, you just hit okay to all the dialog boxes. And after a few minutes, a few seconds, it should show up. All right. So this is what it looks like. I think I showed you the animation last week. What we're going to do is insert parts. So like I was saying, put in 1 copy of the stand, 1 copy of the bearing cross, and 2 copies of the clevises. And I'll hit my green check mark. So the first thing I like to do whenever I start an assembly is to pick one part and just anchor it to a point on the assembly, usually the origin. And all that's doing is making sure that the origin of my assembly, this thing right here that I start out with, I just want to make sure that that is located in a sensible place with respect to the actual stuff in my assembly. Because if my origin's over here and all my work is way out here somewhere else, then if, for example, I'm trying to open this assembly in another assembly, like as a sub-assembly, then it's going to be super weird when I import the assembly and all my stuff is way out in space. So I like to have, in this case, I'll probably pick the base because that makes sense to me. I'll pick the base and anchor that to the origin here. And the way I can do that is pretty simply with a fasten mate, since I don't want the origin to be able to move relative to the base of my U-joint stand. So I'll just pick the bottom center. Doesn't really matter which one do. And the way you create a mate is with what we call mate connectors. So let me show that again. I realized I was just doing it without saying anything. The way you create any mate is the same as any features that we've done in Onshape so far, be that in sketches or in like the 3D space. So I click on fasten, that brings up my little dialog box. I have my fastened mate. And all I'm gonna do is select the points that I want to be touching each other once I complete the mate. So the first point is going to be the bottom of my stand here. And Onshape kind of tries to guess what points you would want when you hover your mouse over an important location on the part. So if I hover my mouse down here on the bottom of my base, I get a mate connector down there. You can see that little icon looks like a circle with a triangle, like a Pac-Man with my coordinate axes on it. That's my first mate connector. And the second one will be on the origin. And you can see when I click the second mate connector, it kind of jumps. My part was over here, now it's over here. Onshape is just giving you a preview of what it'll look like. So if I'm okay with it, I can hit the green check mark. If for some reason something looks off, maybe it's flipped upside down, maybe it's not oriented the right way, I can fix those using these two tools. So flip primary axis, that just inverts. So if it's upside down, I just hit that. And if it's the wrong way, maybe I want it to be along the y-axis, I can just hit this and it'll rotate it for me. It doesn't really matter in this case, right? I'm just anchoring my part there. All right. So the next thing I'll want to do is to put my clevises inside the stands. So when I think about how I want the clevis to be able to move with respect to the holes in the stands, basically I only want it to be able to revolve with respect to the stand, right? They're only going to be spinning. In this case, however, I'm just going to use a cylindrical mate because if you think about it, if the two clevises are at an angle to each other, I'd have to do a bit of like trigonometry to figure out exactly where axially they're going to have to be positioned. Remember the Revolut mate, you kind of have to specify where it is and then it can't move axially anymore. And since I don't actually know how far it has to be, I'm just going to use the cylindrical mate to kind of get away with not knowing what that'll exactly be. And leaving that extra degree of freedom is actually going to be important when I make my later mates, so I don't over constrain the assembly. So for mate connectors, I can just click on this, this rod here. And the other mate connector will be on the inner cylindrical face of the hole where I want the clevis to go in. And it doesn't actually matter which of those like 3 mate connectors that are parallel to each other. It doesn't matter which of those I choose because, as you recall with the cylindrical mate, I can move axially back and forth, and I can also spin. So really, I just need to make sure that I click on the 2 cylindrical faces. And so now this clevis is now inside. It can spin and it can slide in and out. I'll do the same thing to the other one. The cylindrical mate. Just click on the cylinder here, and again on the cylinder there. Now you can see when Onshape tries to show me what it came up with, this isn't quite what I want, right? The clevis is backwards. I need to flip it. So I'll use the tools that I talked about, flip primary axis. And what that'll do is just flip it to be the way I want it to be. So that's 3 of my parts assembled together. I have my stand, and the two forks are now able to spin more or less in position. The last thing I need is to put the bearing cross in to kind of couple the 2 clevises together. And for that, I'm going to use just the Revolut mate. Since the bearing cross, that's never going to like slide out of the clevises here. So for this, I'm just going to hit the end of one of the circular faces, and I'll go up here to the top, and I'll pick, in this case, I'm going to be very careful to pick the top circle here. So not one of these middle ones, but like the top one here. And when I do that, I need to do a quick flip. But this is what I want. I want the cross to be inside of the clevis. And now, whoops. You can see that this, guys, there, you can sort of see it. You can see that it's freely able to spin inside of there. And so the same thing, the last mate I'm going to do is to make this Revolut with respect to the other one. So same procedure. I'll hit the end of the bearing cross there, and I'll hit the top circle of this. You can see when I click on it that Onshape, like before, it kind of jumps your part over to where it's supposed to be, but you can kind of see that it broke the other one. Now these two aren't connected. So that'll happen every time you try to mate a part that's already mated to something else. Onshape will just demonstrate its solution for the 2 parts that you clicked on, but it won't update everything else right away. And to do that, if you want to actually see the full preview of what it's going to look like, you can just tell Onshape to solve for the rest of the geometry. And you can see when I hit solve, it actually updates the other parts to actually meet all of the rules that I set using the mates. So that's all I need. Hit the check mark, and you can see this is what I was talking about with not knowing exactly where the rod is going to sit. If I'd started out with Revolut, I would have had to specify this exact distance for where the rod needs to stick out. And I didn't know that because I didn't do the math. So since I used the cylindrical mate, I didn't have to worry about it. I just left that degree of freedom. And now that everything else above it is constrained, it kind of just works itself out. And hopefully now when I try to click and drag this, what you'll find is that the 2 shafts will kind of rotate together in a coupled fashion. So I'll just animate this guy, and then I'll pause to take any questions or maybe can't animate. Well, in any case, I can spin it with my mouse, and you can see the rotating action of the universal joint. Maybe there's some weird like math thing going on that prevents it from animating, but hopefully you can just see it as I'm dragging it, that the two shafts are coupled. All right, so if you have any questions, if you have any problems making this assembly, let me know, and I can look at it or we can talk about it. If you have any general questions about assembling an Onshape, also feel free to ask. All right. Well, if there are no questions, I'll assume everyone is good with this project, so we can put a close to that and move on to the next thing. All right, so as I said, and maybe hinted at a little bit in the first class, our second project is going to be modeling a little air engine that's designed by littlemachineshop.com. So if you go to their website, you can find a bunch of drawings. I also put a copy of those onto the Google Classroom. So right under the U-joint parts, there's a PDF of part drawings for this little engine that was designed, or that's uploaded at littlemachineshop.com. So over the course of the next 3 or so weeks, both in class and for homework assignments, we're going to have you model the various parts for the air engine. And at the end of the next, say 3 or 4 weeks, we're going to assemble that. So maybe I can show you a completed model that we finished in a previous class. Here we go. Basically, this is what you're going to make. There are 7 parts, or maybe 6. Okay, there's 6 parts. Each of them are pretty straightforward. And at the end, once you've assembled them, what you'll have is this engine. You can see there's like a rocking cylinder here. There's a piston that's driving the rotation of this little cam wheel, crank wheel, I guess it's called. And on the back, there's a little flywheel that rotates. So this is what you'll be making one piece at a time. The very first one, that's homework for this week. So by next week, I want you to try to finish making this part, and that is the base. So this plate at the bottom here, the base plate, just the base maybe. The drawing for that is in this slide, and it's also in the Google Classroom where I uploaded these drawings. So the very first, maybe not the first, the third drawing in that PDF is of the base. So a few notes here. This is more practice in how to read drawings. In this case, these drawings were made by not me. So like it's kind of like a real example of when you might find something online or someone might give you a bunch of drawings that correspond to like a real object, right? People actually make these engines like for hobby or for education out of like metal or whatever in the machine shop. And so these drawings are actually it's possible to follow these drawings in real life and create a working model air engine. So what we're going to do is create like a 3D model on our computers, but the idea is the same. We're working from the drawing. These drawings all have exactly enough information to create the part. In some cases, there are going to be some weird things. I think the base is pretty straightforward, but as we move forward, there's going to be things like tolerances on the drawings. There's going to be things like hole callouts. So we'll go over what all those mean before you have to use them. In terms of the base, though, the only peculiar thing perhaps is this counter bore. So remember, these drawings are meant for people to be able to make the thing in real life. And when you're working in real life, you don't have things like perfect fasten. You don't have perfect glue that can just attach magically different parts together, right? You need to use some kind of fasteners, whether that's nails or screws or bolts and nuts. And so these parts drawings, they're all going to have some kind of accommodation for usually bolts. And so in this first drawing, what you'll see is that these holes are counterbored. And that means that there's a larger diameter hole that kind of goes partially through the depth of the hole. And then the rest of the hole is just the nominal diameter, which is specified. So you can ignore these. I don't really care if you model the counter bores. You can just create a single hole that has a diameter that's listed in the drawing. So you don't have to worry about trying to make this shape. You can just create a single hole that has a diameter of 3/8 and 0.2 inches. If you want to, you can try modeling the counter bore, but in most cases, you'd have to look up in a table like the standard counter bore diameter for a 3/8 hole, right? So if you really want to, you can challenge yourself. I'm sure if you look up something like counterbore chart, it'll tell you what the standard diameter is for the counterbore given a certain hole diameter, but really don't worry about that. It's only if you really care for whatever reason about making this accurate. Here's kind of a demonstration of what they're meant to do, right? It's so that your hardware can sit flush or can sit such that you have like a flush surface above the head of the fastener. Yeah, so don't worry about the counter bore. Otherwise, this part is pretty straightforward. It's basically a rectangle with some holes in it, but you're gonna get some practice with dimensioning things and reading the drawing. And as we go through the weeks, they're gonna get more and more complex. So keep on top of it. That's the only assignment for next week. So when we come back, we're gonna start going over, there's a couple parts that I'll demonstrate and we'll follow along together in class, but a lot of the parts you'll be expected to do kind of on your own, looking at the drawings. So if you have any questions about that, about the homework or anything that's coming up, let me know. I'll stick around for the last few minutes to take any general questions that you have, but other than that, that's all we have for this week. So yeah, see you again. Okay, everyone's gone.
Thank you, Dean. Thank you so much. See you next week.
Okay.
Okay, bye-bye now. Bye.